All right, folks, let's give it a shot. What is the derivative of the natural log of the absolute value of something? 1 over that something. Do I need an absolute value on it? No. What happened in either case before? We just got 1 over x. Then I multiply by the derivative of that something from the chain rule, right? What is the derivative of secant x? Secant x tan x. What do we end up with?
Tangent x.
Tangent x. Okay. Again, that's a nice one to keep in the back burner, okay, for Calc 2. Okay. All right. All right, who watched the video? We've got the Scottish mathematician John Napier invented an early form of logarithms in order to make whose lives easier?
Sailors.
The sailors' lives easier, right? All right, I wish we had time to go through this. We don't. There was an original purpose for students learning logarithms prior to calculus. Okay, so I just want to show you really quickly the basic idea. Okay, so in fact, let's just pause this. But it turns out that they have, being the inverse of the exponential functions, they have a lot of nice properties beyond that. We are basically going to resume that idea of using logarithms to take complicated operations and express them in a simplified format in a process that we're going to call logarithmic differentiation. Okay. Okay, here are the steps for doing so. I'm only going to do one complicated one. All of the rest are a little bit smaller, a little bit faster, a little bit easier. So this is, I'm not saying that this isn't important, because you will have a problem like this on your next exam. Okay? But we only have time for one large example. Okay? All right. So maybe you believe me, maybe you don't. The right-hand side, I think that's a little bit complicated to take the derivative of. Because in the numerator, I've got a product rule, and in the product rule, I've got a chain rule, and in the denominator, I've got a chain rule. Okay? And if you don't think that that's too complicated, and actually it wouldn't be outrageous to ask you to do this one by hand, but if you don't think that's too complicated, just add more factors in the numerator and the denominator, and eventually you would have one that's extremely complex and hard to take the derivative of. Okay? If you haven't tried to take a triple product rule yet, just you wait. Okay? So it does get harder. Okay? But watch what we can do. Because the only operations in here are multiplication and division, and here I'm thinking of powers as also multiplication, I can use my properties of logarithms to break this thing up. Here's the trick. The first thing I do is I take the natural log of both sides. Okay? Step 1, take the natural logarithm of both sides in that sequence of bullets there. Okay? Now, why did I do that? Well, because now I can break up this entire expression. Okay? So don't write this down because I'm going to end up doing it all at once. But let me just get started. In the numerator, I've got a multiplication, right? So I could rewrite that as the natural log of x to the 3/4 plus the natural log of the square root of x squared plus 1. Right? Okay? And keep going, but don't hold on, because I'm actually going to do a couple steps at once here just to save room. Okay? But the 3/4 that's inside there can come out as a factor by my properties of logarithms. Okay? So anyway, I can break up this whole expression, and you do want to practice doing this in probably one step, as 3/4 the natural log of x plus 1/2 the natural log of x squared plus 1 minus 5 natural log of 3x plus 2. let's look what happened here. Okay, so over the multiplication, I broke up the logarithm as addition. Over the division, I broke up the logarithm as subtraction. We okay with that? Anyone want to talk about it? Okay. Then I pulled out this power of 3/4. I pulled out, what's the square root? It's to the 1/2 power. I pulled that square root out. Okay. And then likewise pulled out the 5. Okay. Can I pull this 2 out here? No, because the entire argument inside the logarithm isn't being squared. Only the term is being squared. Same thing over here. Here I've got a multiplication of a 3 and an x. Can I break up that logarithm? No, because it's not one big multiplication problem inside the logarithm. Okay, so this is I think this is as stripped down as I can make this. Okay. Kevin?
Couldn't you technically argue that since it's 1, squaring it would have no effect, so...
Well, you could say that there's a 1 on outside all of that and then pull out that 1, but that doesn't change anything.
Well, no, I just meant because 1... Never mind. It's
No. X squared plus 1. Careful. X squared plus 1 does not equal x plus 1 squared.
But x squared plus 1 squared.
Well,
I mean, I know it's
fine.
not shown, but...
So if you wrote this, x squared plus 1 is equal to x squared plus 1 squared, there's nothing I can do with that. I still don't have the whole expression being squared, because this does not equal x plus 1 quantity squared. If it did, then I could pull out a 2, but it does not.
Okay.
Yeah, great question. Great question. So be careful with that. Okay. Good. All right. Folks, I have stripped this thing down. Now I'm going to implicitly differentiate both sides. I'm not taking the derivative of it because I no longer have an explicit function of y. I've got an implicit function. Okay? So I feel like I've come to a compromise with you guys. You didn't know I was arguing with myself over it. If you don't want to write d dx of both sides, then at least tell me this. Differentiating yields, or something like that, and then do it. But don't go from here to here without any sort of explanation. Okay? So, differentiating implicitly gives me, what is the derivative of the natural log of y? 1 over y times y prime by that chain rule for implicit differentiation. Okay? That equals 3 over 4x plus 1 over 2 times x squared plus 1 times 2x minus 5 over 3x plus 2 times 3. Take a look at those, make sure they all make sense to you. Any questions on that? Okay. That wasn't bad, right? The calculus step wasn't that bad in this process of implicit or of logarithmic differentiation. The worst I had to do was take derivatives of logarithms and then occasionally worry about a minor chain rule. But there were no product rules, there were no quotient rules involved in doing this. Now, they could get so complicated that maybe you'd still have to do that. Okay? But I think that as far as the calculus step goes, this was a lot easier than if we tried to tackle the original question. Now, are we done with this problem? No. Can't I just say that this is the derivative? No, because what do I have on the left-hand side?
1 over y.
I've got a 1 over y times y prime. Okay? So, I'm going to take, normally I would do this in one step, but I'd like to take 2 just to clarify. So we get y prime is equal to y times all of this, and let me clean it up just a little bit. 1 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Any questions about what I did there? Yeah, Chop.
Is that 3x or 3x squared plus 2?
So if we go back to the good question, let's find out. I could have made a mistake. So if we go back to the original, our denominator had this 3x plus 2. Came out like this. We took the derivative of this. We got 5 over that times 3. Am I in the right spot? Is that what you're talking about?
No, you're right. I think I put a squared in here myself.
That's okay. I've had exponents grow out of nowhere too. It's easy to have happen. All right. Now, is this still I've got to solve for y prime. Am I done with the problem?
No. Kind of.
I mean, I've given an implicit answer, but
Technically.
what should I do? What's that, William? Let's replace this expression right here with what y was holding the place of. Okay, I might need a hand on this. Let's give it a shot. Y prime is equal to x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th power. Help me out, folks. Is that y?
Yeah.
Okay. Times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Kind of the nifty thing about this is it already comes out pretty cleaned up, too. I mean, there may be other cases where you could simplify that more, but that's actually comes out pretty nicely. So folks, I only have a chance to do one of these in class. You do have 3 of them on your practice exam, or 3 of them on your unit review. Okay, so you can look at those. Here are the steps. Okay. We first took the natural log of both sides. We broke it up using the properties of logarithms, implicitly differentiated. Then we solved for y prime, not forgetting to back substitute what y stood for. Okay. Folks, some of you are still not naming things on the left-hand side here. If you don't name something on the left-hand side, and then you end up having to do implicit differentiation and then back substitute, you'll drop something. I don't know what, but you'll drop something. Okay? So that's why I've been trying to harp on you all along about naming your components. Okay? All right. Here's just a pause in this question set. How do I take the derivative of x to the x power? I want to think about that. How do I take the derivative of x to the x power? Can I use the power rule? Can I use an exponential rule? So talk in your groups and decide why you cannot use either of those rules. Get your story straight with your group. All right, this group over here in the back, what do we have? What do we have happening here?
My idea was to take basically like the log base a of x, like that kind of thing, but that wouldn't work because they're both x. You don't have an a in x.
Yeah. So, exactly. Why can't we use the power rule here? When do we use the power rule? We use the power rule when we have something like y equals x to the n, where n is understood to be a fixed number. Okay? It might be nice, it might be messy, but it's understood to be a fixed number. Why can't I use the power rule? Because my power is a variable here. The power is changing in this. Okay, so I can't use the power rule. Okay, well maybe I could think of trying to use the exponential rule. I know how to take this derivative now. We learned that on the previous page. Why can't I use this one? Because this requires the base to be fixed. So does everyone see what's happening here? We've got a really interesting function that's an exponent whose base and power changes in tandem with one another. That's kind of interesting. You should try graphing it. Just take a look at it. It's hard to, it looks very exponential, but it's more than exponential. Okay? All right, so here's how we're going to take its derivative. We're going to use the technique of logarithmic differentiation. Hey folks, let me give you just a hint on how I mention things on a test. If I gave you this problem on a test, I would say use the technique of logarithmic differentiation on it, because I want you to use that technique and not try some other method to get there. Because there's lots of ways you could come up with the answer, but I want you to show me that you know logarithmic differentiation on this one. However, on a test, I don't know of any other way other than logarithmic differentiation to do this one, so I won't necessarily give you the heads up, use logarithmic differentiation on this problem, and you just have to recognize it's the only trick I've got for this problem. Okay? All right, so we're going to do logarithmic differentiation. Follow your bullet points from above. What's the first thing I do to both sides? Take the natural log of both sides. Okay? From here on out, whenever you deal with a logarithm, I want you to remember that a logarithm is a handy tool for separating a power from a base. That's how I think of logarithms. I use them as a tool to separate a power from a base. Okay? Why couldn't I take the derivative of this? Because both the power and the base were changing. Well, let's break them apart. Okay? So we get that the natural log of y is equal to x natural log of x. How are we doing? Okay. Now what do? All we've done so far is algebra. Now we implicitly differentiate, so please write something like differentiating. Unless you want to just write, or you could write dx of both sides, but do one or the other. Okay, because if you don't, then your reader thinks there's some algebraic way to get from here to what you're about to write, which there isn't. Okay? So, what is the derivative of the natural log of something? 1 over that something.
You have to change.
Times y prime. What do I have to do over here? What's that? The product rule, right? So here's my first times the derivative of the second plus my second times the derivative of the first. Okay? Good enough? Okay, so we get 1 over y prime is equal to 1 plus the natural log of x. We done with this problem?
No.
Well, heck no. We're supposed to find y prime, right? So we get that y prime is equal to y times 1 plus the natural log of x. Are we done with this problem?
No.
Heck no. That's an implicit answer. We can be explicit about it. Okay? So we get y prime is equal to x to the x times 1 plus the natural log of x. Okay. I think it's worth making just the quick comment here, folks, that if I gave you a polynomial function, f of x is equal to x to the 4th power, its derivative is 4x cubed. Its rate of change is, as for large quantities of x, its rate of change is smaller than the functional values itself. Okay, so it's at 1,000 and it's growing by 400. Or it's at 1,000,000 and it's growing by 300,000. Okay? If I give you the exponential function, its rate of change is its size. Its rate of change is its size. That's really interesting. This function right here, its rate of change is large. It gives out. I mean, it is changing at a rate. So it's at a million, and it's changing by 1.5 million. It's changing incredibly fast. Okay, but it's not quite. It's not infinite. It's still measurable. Okay. Anyway, that's something to think about. That's not something I test you on or anything. But that's something to think about. All right, but what I could test you on is this part right here, finding the derivative of x to the x. Okay? All right? So we left a few things unproved in this class. There's plenty we've left unproved. Okay, let's pick something up that we missed early on. Okay? We've been using the generalized power rule for a long time now. Okay? Let's actually prove that. So be careful here. I'm sort of backtracking. I'm back to n being just a natural, or sorry, not a natural number, a real number. But it's a constant. It's not a variable here. Okay? So let's go ahead and take the derivative of this. But I can't use the power rule because we don't have it yet. So what could we do? Well, we could take the natural log of both sides. I'm going to do this in one step. Everyone see what I did there? In one step, I pulled out that n in front of the logarithm. Okay. Implicitly differentiating 1 over y prime is equal to n over x. There's not a product rule there, right? Because n is just a what? Constant. And so it just comes along for the ride. So all I'm really doing is taking the derivative of the natural log, which is 1 over x. Okay? How are we doing, folks? If I've lost you, it's my fault. So stop me. Yeah, yeah, so we okay from here to here?
Yeah.
Okay. So now I'm taking the derivative. Okay, are we okay with the left-hand side? Okay. So on the right-hand side, this n is just a constant, so it comes along for the ride, right?
Yeah.
And then what's the derivative of the natural log of x? It's just 1 over x, right? But then n times 1 over x I could just write as
Just n over x.
n over x. Good. Okay. Solve for y prime. Okay. We get y prime is equal to n over x times y. But what was y? X to the n. And clean it up. This x is to the minus 1 power times this x to the n power. You add their exponents, you end up with x to the n minus 1. There it is. Da, 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 da. The power rule. It's pretty cool. All right, so for example, I could say that g of x is equal to, that's x to the pi. What is g prime of x? With no hands, it is pi x to the pi minus 1. Right? Even though pi is just, it's some messy real number, it's not a nice natural number, that's how we take its derivative. Now be careful, I'm changing. This is a completely different problem now, right? Can I use my generalized power rule on this? So you're shaking your heads. How come? There is a chain rule in the exponent, but that's true, and that's going to come into play. I'm looking for something a little bit more.
In the exponent.
What's that?
There's a variable in the exponent.
There's a variable in the exponent and a variable in the base. Both of these are variable. So I can't use any power rule or exponential rule. Instead, I have to use logarithmic differentiation. Okay? Let's do it real quick. Let's do it real quick. So we get y equals x to the cosine of x. So the natural log of y is equal to the cosine of x times the natural log of x. We getting the hang of this logarithmic differentiation? Admit it, it's kind of fun. Right? Come on, you guys are in calculus class. You're nerds now. You can admit it. Okay? It's a little bit of fun. Differentiating gives 1 over y prime. This is a kind of a plug and chug procedure now. What do I have to do though here? What's that, Maria?
Product.
I've got to do a product rule here, right? So here we go. It's the first times the derivative of the second plus the second times the derivative of the first. Okay? That gives us y prime is equal to x to the cosine of x times the cosine of x over x minus the sine of x times the natural log of x.
Like what?
I did that.
To the way.
I multiplied the y over and then replaced it with what it was. Sorry, I did both those steps at once,
Okay.
right? So, oops, that's not red. So that's where this x cosine x cropped back in. I just did, and you're welcome to do that step all at once. Of course, you know whether or not you make mistakes, and you know whether it'd be best to just do it one step at a time. Okay? Are there questions on that? Ashley, how are we doing? Good? Tiernan? Cam? Daniel? William? Lauren? Anybody want to stop, pull the brakes before we move on? All right. Folks, I just want to talk about this really briefly. Okay? I feel like you shouldn't go forward in calculus until you hear this expression, until you learn about this idea. Okay, so we're going to spend just a moment to talk about it. So, calculus is a language that was developed to work with the physical world around us. So you might think that the most important type of math for scientists is calculus, and that's sort of true. But in reality, what scientists do is they solve differential equations. Okay? That is a large portion of what you're doing if you're a scientist. Why is that? Well, first of all, what is a differential equation? A differential equation would be something that looks like maybe this. Y double prime minus y equals 0. That's an equation, right? But what is the unknown thing? It's not a number. What's that? The unknown thing is a function. So in algebra, what do you learn how to do? You learn how to solve equations to find the numerical value that would make it true. In differential equations, you solve equations to find the function that would make it true. And specifically, differential equations not only have an unknown function, but they have derivatives of that unknown function, because in the real world, you don't know what a thing is until it changes. I mean, we can't observe anything until it changes. You can't observe a color until you can contrast it with another color, right? You can't talk about how the days are changing until you can say, okay, today it was 20 degrees, tomorrow it's 25 degrees. I can talk about how the day's temperature changed. Okay? So that's how the real world works, is you don't measure the thing, you measure how it changes. Which means we get differential equations arising all the time in natural phenomena. Okay? There's a whole, there are gobs and gobs of courses you can take on differential equations. Oh, we offer one here. You should sign up for it in a little bit. I teach it. Okay? Take Calc 2 and then you can move on, or maybe it's best to take Calc 3 and then take it. Okay? But so there's a whole field of mathematics about solving these types of equations. It's actually really elegant and interesting, and the types of story problems that you can solve are just amazing. Okay? So here's the most basic differential equation that's of any consequence to the real world. Okay? So there's this phrase that the growth rate is proportional to the population. The growth rate, oh, that's a derivative, right? Because it's got the word rate in it. The rate at which something is changing is proportional to the amount you have. There's a lot of stuff that obeys this rule. Okay? On a limited scale, most organisms, I'm thinking like bacteria, grow like this. If I have one cell, I would expect that bacteria culture to be growing very, very slowly. But if I've got 1 million cells, I would expect it to be growing quickly. And if you look at the way mold grows on your milk jug, maybe you've done it in a biology class. That's a little okay. You watch the mold and you see how quickly. So it starts off in first day nothing, second day nothing, third day nothing, fourth day there's a tiny little blue speck. Fifth day that blue speck got a little bit bigger. And then all of a sudden it's growing how, actually? Exponentially, and I'm not using that term colloquially, literally exponentially. Exponential growth means it follows this model. And it turns out that a solution to this equation is y equals c naught e to the k times t, where t is my variable there. Because, let's check this. If I take the derivative of this, what would I get? I get y prime equals c naught e to the kt, but then by the chain rule, I'd multiply by another factor of k. And so what is y prime? It's the same as the original function, except it's got this times k on it. That's what this says. So my guess is the majority of you have seen this equation many, many times before. You saw it in college algebra when we talked about exponential growth and exponential decay. If you haven't seen it, don't feel bad. Okay, just there it is. Now you've seen it. Okay, but it has a lot of applications. The thing is that it's introduced to you in a college algebra setting or in your earlier math career as here's this equation. Where did this e come from in this problem? Well, it comes from this differential equation to begin with, that the rate of change is proportional to the original amount. And the solution to this is an exponential expression. Yes?
So why isn't it a value of y to t if there's no variable for t in the equation?
That's a great question. So y is a function of the variable t. So we usually don't write that. What I wrote here was shorthand. We usually wouldn't write this, but this is what I'm looking for. I'm looking for the function that satisfies this. So it is a function of t.
Okay.
I could have used x, but we like t because usually in differential equations the independent variable is time. Yeah. Okay. All right. So I just want to say this. If the k value is positive, the function exhibits exponential growth. And if it is negative, the function exhibits exponential decay. Okay? By the way, this is literally what we mean by exponential growth. I have it's kind of a pet peeve when somebody says, oh, the population of Colorado is growing exponentially, when all they really mean is that it's getting big fast. Okay? Exponential growth requires that it fits this model. So correct them when you hear them say it wrong. James.
What does c naught e mean?
Okay, so E is the Euler's function that we've been using. C naught is just some constant that we haven't yet specified.
Not like a specific population size.
It is a specific population size, and in fact I used the subscript naught because we could see that it's the initial population size. Okay, to be honest, folks, I'm going to park it there because this is not something I'm required to teach you. I wish it was, and we got so much other stuff that I'm supposed to show you. But I feel like I'd be doing you a disservice if you took a calculus class and never once saw a differential equation. Okay, because for the scientists and the engineers, it is the next step. Okay, solving differential equations. All right, so we're actually going to park it there because I think the rest of this is examples related to that, and we don't need to cover it, so we won't.